Okay, so like I mentioned before, since we just finished the last chapter, I thought maybe we'll spend some of this time here in lab since we have it to kind of go over some of the chapters we went through, some of the topics, some of the equations, those type of information, which will hopefully help you with your finals coming up, which once again is next week. So again, we open up on Tuesday with our lab final, and I think that is 10:30 in the morning. And then on Thursday, we have sort of the lecture final, and that is 7:30 in the morning. So early one on that one. Yeah. All right. And then you go home and sleep after that, I suppose. What we're going to do is just going to kind of run through the chapters, whatever comes to my head, I suppose, from these chapters. Again, kind of the main things we talked about and some of the equations and formulas and stuff that we saw in some of these chapters. All right. So, and obviously at some point we will stop and check out our lab lockers and all that kind of stuff as well. All right. So we started here 15 weeks ago. I know, hard to believe, here. There we go. So perhaps it was chapter 12, I think, maybe kinetics, somewhere in that ballpark. So we opened up talking about kinetics in this class. And when we talk about kinetics, as we mentioned there and along the way, and what we just talked about as well, kinetics deals with really how fast or slow sort of a reaction takes place. As we talked about when we got to thermodynamics, that it really takes care of the idea of whether or not a reaction will take place. But it's really the kinetics, right, that tells us how fast or slow a reaction takes place. We talked about the idea of rate, and when we talk about rate, typically in terms of reactions, what we're looking at are something like molarity over seconds. Really, we're looking at how the concentration of either a reactant or a product is changing with time. And with that being said, one of the first things that we talked about is in terms of kinetics and sort of figuring out those type of things is what is referred to sometimes as the rate expression, right? And that rate expression is based off of like an equation here. And we could write several rate equations or expressions based on an equation. And we could do something like the rate is equal to minus 1 over A, change in the concentration of A over the change in time. Remember that with reactants, we do expect that over a period of time, their concentrations should start to decrease. And that's why we need the negative here when we're dealing with reactants. Remember as well, why doing this, this is what takes into account the coefficient and the mole-to-mole relationship kind of together. So you don't have to do like a separate stoichiometry problem and a kinetics problem when you're doing this. You could kind of combo it together by taking 1 over the coefficient. That'll get you the proper mole-to-mole relationship and everything that we talked about. Change the concentration of A over change of time. That obviously in most cases when we do a change of concentration is our final concentration minus our initial concentration. And obviously for our change in time, right, is like our final time minus our initial time as well. We could set that equal to minus 1 over B, same reasoning for our coefficients, change the concentration of B over the change in time. And then when we get to our products, because they are increasing with time, we don't need the negative in front of these, right? So there is no negative in front of this. We're going to go 1 over the coefficient, the change in concentration of C over the change in time equals 1 over the coefficient of our last product here, D over the change in time. The reason, again, that we do not have any negatives on our products is it is increasing with time. So when you do this calculation of final minus initial, you will get a positive number. The reason why we do need the negative for our reactants is because it's decreasing with time. So when you do this calculation, you will get a negative number. And remember that the one thing that you should always have is when you calculate the average rate of a reaction, it should be a positive number. So it should be a positive number, that number. And that is why we have the negatives there really for our reactants to turn that change in concentration from negative into positive. And when we have our products, we don't need it because we already have a positive number in that particular case. Because they are all set equal to each other, this allows you that if you know really just one piece of information about anybody in that reaction, you could relate it to somebody else. So for example, if I knew something about A, I could take my rate expression for A. And if I knew something about D, I could take my rate expression for D. And again, or maybe I didn't know anything about D, but I definitely knew this guy. I could use that to figure out the rate. And again, that rate is going to be the same rate that we have over here. And that would allow us to figure out, for example, how like D is changing with time. So as long as you know really one piece of information in this scenario here, either the average rate, how somebody's rate of appearance or rate of disappearance, you can basically figure out how everybody else in that reaction is changing with time. Remember that if you did calculate, for example, in a question, how A is changing with time, you will actually get a negative number for that because, again, it's decreasing with time. And if you did something like D, which is our product, you will get a positive number. So depending on if you're talking specifically about your reactant or product, you may get a positive or negative value depending on if it's the rate of appearance or disappearance. But when you're talking about the average rate for the overall reaction, that should always be a positive number. So again, those are things you want to remember on that. Now, any questions on that there? Okay, then we got into kind of rate laws, obviously. And when we talk about rate laws, they are a little bit different than a rate expression. Remember, rate laws, a couple things about them, right? They only deal with reactants. So only reactants are in the rate law. They're also only found experimentally. So they're found experimentally. And these guys up here are orders, right? We could calculate the overall reaction order by adding those together. So if we add those together, it gives us the overall order of this particular reaction. Remember, the orders really are, if you want to think about it, sort of the proportion of each of those that you need to sustain a particular rate of a reaction. Also, depending on the orders of each reactant, one reactant can have a greater effect on the overall rate than, say, another. So, if we had a rate law where each of them were first order, that means if we, for example, had 2 molar of this guy and 2 molar of this guy to start with, that would give us a rate that's like 4 molar seconds. Again, if we wanted to increase the rate of this reaction, we could simply actually increase either one of these. So we could increase this to, say, 4 molar, and that's 2 molar. That would give us a rate that's basically 8 molar seconds. So by doubling one reactant in this case, we're able to speed up the reaction by a factor of 2. And vice versa, if you were to cut one of those reactants in half in terms of its concentration, it would also cut the rate in half as well. So it'd be able to slow it down. Now, obviously, as we talked about, if the order is a little bit different and maybe say one is second order, it would have a bigger effect on the overall rate. So if I had 2 molar for each of these guys, that'd be 2 squared, which is 4, and 4 times 2 is 8 molar seconds. So just by this guy going from first to second order, if we had a different reaction, our beginning rate is actually a lot longer or faster. And if I doubled the concentration of my B in this example, 4 squared is 16. 16 times 2 is like 32, I think, molar seconds. So in this case, by doubling the reactant that has a second order, our rate actually goes up by a factor of 4. So it's going to get super fast, right? So it's going to go really, really fast by doing so. We could still affect it if we wanted to by just increasing A. We won't get as big of an effect, but that would also obviously make it go quicker. And obviously, again, if we cut the order or the molarity in half, we will also slow down the reaction. The other thing we talked about, remember, is that if we did have a order of 0, that does equal 1, basically, right? And if you have something that has an order of 0, you can pretty much do whatever you want to that particular reactant. You can increase the concentration, lower the concentration. It will really not have any effect on sort of the rate of the reaction. It would all be dependent, for example, in this one of A would be the only thing that could kind of affect the rate. Remember that the rate constant kind of tells you basically, how fast or slow the reaction is happening. So if you have a larger rate constant, typically it'll kind of go a little quicker. If you have a smaller rate constant, it'll be a little slower. Now, because these rate laws and orders and everybody are found experimentally, that means typically, as you probably remember, you are typically giving some tables here of initial concentrations for different experiments and rates, right? And you got maybe like experiment 1, 2, and say 3. And maybe this is like 2 molar, 2 molar, and like 1 molar and 2 molar. And this is like, maybe this is 4 and 2. We'll just keep the number simple. And then maybe we'll go 4 molar here and 1 molar there, and maybe, this is 2. I'll go 8 here. So maybe you got some type of table like this. Remember that we could use this information to actually figure out the orders. Most of the time, as we talked about, you can kind of do it mathematically. That's the rate of 2 over the rate of 1 equals k a to the x and b to the y. K, a to the x, and b to the y here. Remember that 1 and 2 here doesn't mean that you just go and choose the first 2 entries. What we're looking for, right, is to keep our unknowns to a minimum. So we want to choose 2 entries where one of the concentrations remain the same and the other varies. So here, if we did like experiment 1 and 2, my made up one, we could do the larger rate typically up on top because that will usually give you a little bit more whole numbers. You could do it the other way, but usually if you want kind of nicer numbers, put that larger rate up on top. And we would put in our information here. And then obviously that's everything from experiment 2. Everything from experiment 1 would go up on top. And we'll see how bad I did on this. Hopefully not too bad. And we'll go Y. So that would give us a 2. These are rate constants, which should cancel out. Although we don't know this order, it should be the same. So that should completely cancel out. And that will give me a 2 to the y. And y in this case is going to be equal to 1, right? And that would give you the order for y in this example, or b really. And now what we would do is we would go back to that table and we would choose 2 more entries where b stays constant and obviously a varies. So in this case, we could do something like experiment 1 and 3. Again, taking that larger rate up on top, we do have to keep everything together in terms of the values for that experiment. But on the bottom here would go 2. We would go our 2 there and our 1. I might have did it right here. We got a 4. Those guys will cancel. That'll give us a 2 to the x, and those guys would completely cancel. X in this case would be 2. So that would give us really our order for this reaction. The rate would be equal k a squared and b. The overall order here, right, would be 2 plus 1, which is third order. And remember that once you figure out the orders and for this particular reaction, you then can figure out the actual value of the rate constant. For example, here we would rearrange and k would equal the rate is divided by a squared and b. Remember that it doesn't really matter which one you choose. Ideally, they all should give you the same answer, maybe even in my made up one here. So we'll go with 2 molar seconds divided by 2 molar squared and divided by 1 molar. Now, if we do this here, we're going to get 2 divided by 4, basically, and get a 0.5 units here, molarity on top, and one of them will cancel. 1 over molar squared seconds would be our units. R m to the minus 2, s to the minus 1. Again, there are ways you could do that. By the way, as we talked about, that is a third order reaction. That's 3 letters. So 3 letters, third order, 2 letters, second order, 1 letter, first order, right? So remember as well that if you maybe didn't pick the larger rate on top and you did the smaller rate, you'll get more decimal numbers. So when you get to something like this here, that if you don't have pretty numbers or you have decimals or you're not really sure, you could solve this by taking the natural log of both sides and then dividing it to the other side, and that will give you your y is equal to 1 in this particular case. So if you don't get really pretty numbers on both sides there, you could take the natural log of both sides, divide it out to get what you need. Any questions on how to do that there? All right, then we got into, I think, more specific types of reactions. And remember, common sort of orders of reactions. We have our first order, we have our second order, and we have our zero order, right? And the reason for this is really, as we talked about, in most reactions that you see, you have pretty much 2 reactants, maybe 1 reactant, maybe 3. You typically don't see reactions where there's like 4 or 5 reactants all reacting at once. And remember that, typically speaking, if each of a reactants are like first order or something like that, you might get a second order overall reaction. Now, each of these do have specific sort of properties that are really important. So let's start with first order, which we just reviewed there in nuclear chemistry. But again, a reminder that when we talk about first order, the most important thing in terms of that, in a sense, is the units associated with the rate constant. Remember, that is typically 1 over seconds. It does not have to be seconds, but it should be really 1 over some unit of time, basically, right? So if you have some 1 over unit of time, that is typically going to be a first order reaction. That's important, as you probably remember, that most of the time, or a lot of times in kinetics problems, they do not tell you in flashing lights, this is like a first order reaction, or this is a second order or zero order reaction. So a lot of times what they'll do is give you the value of the rate constant with its units, and they assume that you know, based on those units that you see, what the order of the reaction is. So with first order, 1 over time is it. 1 over seconds is very common because we do reactions or experiments where we measure time in seconds. It has an integrated rate law of the natural log of A is equal to the natural log of A naught minus KT. Remember that this is basically your time and concentration, how they change sort of equation. Also our half-life equation, which is our natural log of 2 divided by K. Remember that kinetics is all about graphs and all those fun graphs that you made right along the way, that you can rearrange this guy into the natural log of A is equal to minus KT plus the natural log of A naught. That gives you this equation in the form of a straight line, y equals mx plus b. And that gives us our very common graph that we associate, our linear relationship that we associate with first order. And that is the natural log of A versus time should yield you a straight line with a negative slope. And as you can see here, the slope is equal to negative K. Remember that that means that your rate constant should be a positive number because the line there is a negative line, and that will give you a negative slope. And the negative here for the slope value and the negative here will turn the rate constant into a positive number. So you want to make sure you do that. Remember that we also saw another graph associated with first order, but it was not the linear relationship. Concentration of A versus time again gives us that decreasing concentration over a period of time. So really, those are sort of the 4 important things, right, from first order. Definitely identifying the rate constant in terms of its units allows you to know that you should be using the first order kinetics and our half-life and the graph associated with it. Clearly, as we just saw in the chapter we just finished, this is also important in nuclear chemistry, as all radioactive decay follows pretty much this order of kinetics. We also talked about second order reactions, and second order reactions has a different sort of K sort of situation. It typically has 1 over molar seconds. Once again, here the unit of time does not have to be seconds, but it can be any unit of time in that particular case. You could get a second order reaction by having one reactant that is second order. You could also get two reactants where each one is first order, right? Will give you an overall second order reaction. You could also have two reactants where one is second order and the other one's zero order. Will give you a second order reaction. Once again, the identification of that being your second order with those units gives us our integrated rate law, which is 1 over A equals 1 over A naught. Obviously, A naught is our initial and A is our final. Remember, this one is plus KT. This has a half-life equation of 1 over K times the initial concentration. So unlike first order, which is independent of your initial concentration, here with our second order reaction, it is dependent on the initial concentration. And in this particular case, obviously, if you have a higher concentration, when you divide it, you're going to take a larger number on the bottom divided by a smaller, and that will affect, obviously, the half-life. Once again, rearranging this guy in the form of a straight line will give us something that looks like this. Again, that's our y is equal to mx plus b. That means that the typical graph that we associate with second order on the y is 1 over a, on the x is our time. This again will give us a straight line, but different is going to give us a positive sloping straight line. And the slope here will equal k in this case because it is a positive sloping line. So once again, much like the first order, if it is a second order reaction, you do want to use this kind of time and concentration equation and perhaps the half-life. As we saw with nuclear chemistry, really with each of these, sometimes you do have to use both of these guys together again to solve an equation or a reaction that you may be dealing with. Most of the time, if you're going to be using them together, you're probably going to, much like we saw with nuclear chemistry, use the half-life equation to figure out like the rate constant or something like that. Any question on those two there? The last type of order that we specifically talked about was zero order. And zero order is a way you can have one reactant that is to the zero order, and that obviously will give you a zero order. The rate constant in that case is actually going to have units similar to the rate. It's going to be molarity over seconds, or again, some unit of time on the bottom there. We have an integrated rate law, which is our concentration is equal to our initial concentration minus KT. Very similar to first order, except no natural logs going through. So basically identical to first order, no natural logs. The half-life here also dependent on the initial concentration, gives you initial concentration times 2K. So again, the initial concentration here does play a role in the half-life. Rearranging this one very much like we did the others will give us our straight line equation of y is equal to mx plus b. So the typical graph that we associate with this is the concentration of A versus time on the x, going to get us a straight line with a negative slope, and the rate constant will equal basically minus the rate constant will equal the slope in this case. Any questions on that one there? Now, what we then talked about was some energy, right? And the relationship of temperature on the rate of the reaction. And we talked a little bit about some energy diagrams such as this. our reactants and our products, and obviously our reaction progressing this way. And remember that in order for reactants to get the products, there has to be a couple things that occur, including collision. So they do have to collide with each other, the reactants. They have to collide with each other in the correct orientation and in the right spot and with the right amount of energy. And that right amount of energy is typically the hill that the reactants has to climb to get to the other side. That is our activation energy. And in this case, this is going to be a exothermic process. And this is an exothermic process because our reactants are higher in energy than our products. So the only way for our reactants to get down to our products is energy has to be given off. By the way, we also know that because we could calculate our thing that we like, which is the energy difference between the reactants and the products, which is our delta H, right? Our change in enthalpy. Change in enthalpy of a reaction is the delta H of our products minus the delta H of our reactants. And in this particular case, we just look at the graph. Our reactants are higher in energy than our products. That means that when we do this, we're going to take a smaller number minus a larger number, and that typically will yield us a negative value for delta H, which is why this is an exothermic reaction, because ultimately it will give off that energy. Depending on the hill that the reactant has to climb to get to the other side, if it's a larger hill, then it's going to be probably a slower reaction. There's going to be less proportion of molecules that have enough energy to get to the other side. If it is a smaller hill, then there will probably be a greater proportion of molecules that could get to the other side, and the reaction rate would probably increase. Remember that as you go towards the top here, we are breaking bonds, and we are also making bonds till we get to the top there, which is the top of the heap, and that is what is referred to as the transition state. And remember that there's a transition state complex, which is what that is sometimes referred to as the activated complex. And that is a very unstable type guy at the very top of the hill, because in chemistry, right, if it's high in energy, it's unstable. We want things in low energy. So very quickly, this guy will typically kind of drop down to the other side and make our product. So it's very hard to isolate a lot of times that sort of transition state complex. That's our exothermic sort of energy diagram that we talked about. Remember, we have an endothermic, which is similar, except it looks a little something like this, perhaps. And this is endothermic because our reactants are lower in energy than our products. So you got to put energy in there to do that. This right here would be our activation energy. You could also see it's a bigger hill to climb to get to the other side, which is maybe why it's endothermic. And again, we could also calculate our difference in the energy of our products to our reactants. And that gives us our delta H of our reaction. Again, in this case, when we calculate our delta H of our reaction, take in our products minus our reactants. Here, our products are a higher temperature, so we're going to take a larger number minus a smaller number, and that's going to yield us our positive value for delta H that we associate with a endothermic reaction. Remember that there's one way that you can speed up a reaction, for example, and that is to add a catalyst, right? And when you add a catalyst, that finds an alternative pathway, a more efficient pathway for that reaction to take place. And ultimately, what a catalyst does is essentially it will lower this activation energy. And by lowering this activation energy, what that essentially will do is it will allow a greater proportion of molecules to have enough energy basically to get up and over to the other side. And that usually will result in your reaction occurring faster. Now, remember that if you do increase the temperature, typically your reaction rate will increase as well. And if you lower the temperature, your rate of reaction will decrease. A kind of 10-degree increase in temperature, usually in a lot of cases, is enough to double the rate of the reaction. And obviously, if you're going in the opposite direction there, in terms of the temperature, it would lower it. Any questions on that there? All right, we actually saw the Arrhenius equation, which is that guy that we can use to calculate activation energy and all that kind of stuff. We saw two versions of this. We have the natural log of K is equal to minus E of A over R, 1 over the temperature plus the natural log of A. This is sort of the graphical version of the Arrhenius equation. This is Y is equal to mx plus B. And that means that the graph that we typically plot on this is the natural log of K over 1 over the temperature, and that does need to be in Kelvin in this case. That typically will give you a negative sloping line when you do that graph. And as we can see here, the slope of that will equal minus E of A over R, R in this case being the 8.31 version there of the gas constant. And you can graphically determine the activation energy by doing that. And we did that in a couple of experiments, I think, as well. And you can figure out the activation energy as well. You could also figure out something else that we talked about there, which is A, and that's the frequency factor. The frequency factor is sort of that proportion of molecules that have enough energy basically to get up and over to the other side. And that is going to be equal to the y-intercept. So the y-intercept would equal the natural log of A. A little e of both sides will give you the frequency factor. Typically, the units associated with the frequency factor are the same as the units of K. So whatever the rate constant units are typically the same units that we see when we are doing our frequency factor. Now, if you are not interested perhaps in graphing this, or maybe you only have 2 points that are technically on that line, you could sort of mathematically calculate those things like rate constants, temperatures, activation energies, and you could use our natural log of K2 over K1 is equal to our E of A over R, 1 over our temperature minus 1 over our second temperature. Remember that these need to be in Kelvin, obviously. And there's a few different versions of this equation, including a different one, I think, in the lab manual. Sometimes, again, they distribute the negative out and kind of combine some things in the parentheses. But this is the one we kind of went with. And this will allow you pretty much, like I said, if you know both rate constants, both temperatures, you could plug in there and figure out the activation energy. If you know the activation energy may be 2 temperatures and 1 rate constant, you can figure out the other rate constant, or you could even figure out a temperature here. So this is more of the mathematical approach to figuring out those things. The sort of last thing that we talked about here in this kinetics chapter is reaction mechanisms. And what we talked about when we talked about reaction mechanisms is the idea that not all reactions do occur in a one-step fashion. So again, it may be multiple sort of processes that occur that give us the overall reaction that maybe we're looking for. So for example, here, if we were to add these together, anything on opposite sides of the reaction will cancel out, and everybody on the left will stay on the left, and everybody on the right will stay on the right in this case, if we add together. When we look at mechanisms, these are plausible ways that a reaction could take place. It's not necessarily always the way it could happen, but it's a possible way that a reaction can happen. Remember that in order for a mechanism to be good, you basically need 2 things to sort of happen. You need to make sure that all the steps are really the elementary steps. Add up to the overall reaction. Secondly, the rate determining step are the RDS, which is the slow step in the mechanism, should match the experimentally found rate law. So if you remember, we had a number of problems where we're trying to decide whether or not a mechanism is good or bad. And these are really the two things that you want to figure it out. Remember that when you're looking at a mechanism, you know, it may be labeled slow or it may be labeled fast. And the slow step is always the rate determining step. The other thing is you can also write, and this is the only place, for example, if you had a elementary step such as this, and you wanted to write rate laws, this is the only place where you can use the coefficients as the exponents. Remember, you cannot do that normally because you got an experimentally found that. But if you're doing an elementary step in mechanisms, you can use the coefficients as the exponents when you write it. This guy would be the rate is equal to K, A, and B. Again, if you're not doing a mechanism, you cannot do that. And this is the only place you could do that. The other thing that we sometimes saw was you could have a reversible type of situation happening on one of the steps, and you could write a rate law going in both direction, like the rate is equal to Ka squared, and going in the reverse direction this way, the rate would equal K times C. Remember that this rate and this rate are the same, so that allows you to put them equal to each other. And a lot of times we need to do that where we have to substitute out in a elementary step a intermediate. And remember that an intermediate is something that's made early on in the mechanism that gets completely used up and is not present in the overall reaction. So when you have a plausible mechanism and maybe got a reversible reaction, and you look at the slow step, there may be an intermediate in there. And remember, this is how a lot of times we could set these guys equal to each other. And we could use that to solve for whatever we want to solve for to kind of substitute out that intermediate. Any questions on kinetics? All right, then let us roll to the next chapter, which I think was chapter 13. And in chapter 13, we started into our journey through equilibrium. And obviously, equilibrium, as we've talked about, is based on reversible reactions. And when we have a reversible reaction, as we've talked about a number of times, there is basically two directions. There is a forward direction and there is a reverse direction. And remember that essentially, if you're just starting out and you have only reactants, you pretty much can only go in the forward direction, and the forward direction will predominate. At some point, you'll build up enough products that it will come back the other way. Those products will recombine and make the reactants. And remember that when we reach chemical equilibrium, what we are talking about is the rate of the forward direction will equal the rate of the reverse direction. So again, remember, it is not equal to each other. We don't have equal amounts on each side. So as we talked about, what that will essentially do is once it reaches chemical equilibrium, it locks everybody into place in terms of their concentrations, in terms of their pressures, because as soon as you make products, it goes right back to reactants. So it just has a tendency to just keep everybody where they are in terms of their concentration and molarity, or again, if you're dealing with pressures, their partial pressures as well. You could write an expression for this, which is basically the concentration of our products divided by the concentration of our reactants. More specifically here, K would equal the concentration of C to the C, D to the D, divided by A to the A and B to the B. Remember that we do use the coefficients here for our equilibrium expression, and it is products over reactants. When we do it for concentration, this is sometimes referred to as our Kc expression, C for concentration. Clearly, if these guys were gases, we may be looking at pressure rather than concentration. So you could write a similar equilibrium expression dealing with pressures, partial pressure of C to the C, partial pressure of D to the D, divided by the partial pressure of A to the A, and B to the B in this case. This is known as Kp. Typically speaking, when we are dealing with concentrations and pressures, concentrations typically in equilibrium situations should probably be molarity. And if you're dealing with pressure, especially if we're going to do ice tables later, they should be in atmospheres is typically the units that we do that. Typically speaking, Kc and Kp are not the same value, but they do tell you kind of the same thing. Remember that K is just a number, and if we have a large value of K, that means when we reach equilibrium, we should mainly have products present. Again, just mathematically, larger number on top, smaller number on the bottom gives us a larger value. Now, if we have a small value of K, that means when we reach equilibrium, we will mainly have reactants. Again, larger number on bottom, smaller number on top gives us a larger number. Remember that what is considered a large value of K is that big number 1 is considered a large value of K. So anything above 1 is considered large, anything less than 1 is considered small. As we've seen in all those chapters and stuff that we talked about, there is various degrees of that. There is extremes, like we've seen some to like the -34, super small. We've seen some K values like to like the -40 or something like that, which is a really, really large number. And we have K values anywhere in between along the way. Now, depending on what's given to you, clearly you do need equilibrium concentrations or equilibrium pressures to go into each of these. And if maybe you are given the pressure, but you want the Kc, or maybe you're given concentrations and you want the Kp, there's that equation that relates the two. The Kp is equal to the Kc RT delta N. Remember, this is our Kp value. That's our Kc value. The R here is the same R that we use in the gas law, the ideal gas law. So that is our 0.08206 version. That is our temperature in Kelvin. And remember that the delta N is the change in the number of moles of gas. So delta N here is basically the moles of products minus the moles of reactants. And these are gas molecules that we're looking at in this case. So obviously you just subtract those two. We also talked about the importance of doing that subtraction correctly. Remember, you do not just want to take the difference. So if you had, again, let me do this right, 2A goes to B. The delta N in this case would be 1 minus 2, which is -1. Again, the negative is really important mathematically when you go in there. So you do not want to take just the difference. If it's positive, obviously go positive. But if it is negative, you got to keep that so that you do the math correctly. So this is a way you can go back and forth between Kc and Kp if necessary. And again, if you have a large value for Kc, you also have a larger Kp, and a small Kc and a small Kp will also go together. Any questions on that there? We then also talked about what we do when we manipulate some of these equilibrium reactions. As just we were talking about, not all reactions happen in a one-step process. So sometimes you do need to move around an equilibrium reaction and the effect on the equilibrium constant. So just a reminder that if we have our A plus our B going to our C plus our D, And we would have our K in this case, again, C to the C, D to the D, and A to the A, and B to the B. Now, if we reverse this reaction and we flipped it around and went C plus D to our A plus B, the effect on the equilibrium constant is, in this case, we would have K is equal to A to the A, B to the B, C to the C, and D to the D. The difference as you go from here to here, it is 1 over K. It is the inverse of it. So if you reverse a reaction like this, move your reactants to products, products to reactants, you take 1 over the K value, and that will give you the value that you need. Now, let's just say, for example, here I multiplied everybody by 2, and I had like 2A plus 2B goes to 2C plus 2D in this case. The equilibrium constant here would be A squared. I'm not A squared, C squared. D squared divided by A squared and B squared. And if this was 1 for all these guys, like we'll maybe assume, as we go from here to here, we actually squared it. So if you need to multiply by a common number, you take K and you take it to that common number. If you multiplied it by 3, you would cube the K value. If you multiplied by 4, you would, obviously take it to the 4th power. That also means that if I went through and divided by a common number, that would give me A plus B goes to C plus D. That would give me K is equal to the concentration of C, concentration of D, A, and B. And as we go from here to here, that is the square root of K. So if you divide by a common number, you basically take that number to the K. If you multiply by a common number, you take K to that number. If you reverse the reaction, you go 1 over K. So those are very common ways that we kind of manipulate the K value. The other really important thing in terms of that is if we were to add together. So we had 2 equations. And I'll just write it, I'll squeeze it in here, K1 and K2, whatever those equilibrium values are. And if we add this together, again, we get our A plus B goes to E plus F. If we wanted the K value of this guy, K would equal K1 times K2. So remember that if you add together multiple reversible type reactions or equilibrium reactions, and you have the equilibrium constant, you definitely multiply the K values together. You do not add them, so you want to multiply them together. Any questions on those manipulations there? We then talked about our friend Q, which is our reaction quotient. And the Q is calculated the same as K. So for Q, it is still the products over the reactants. And if we're looking at our same equation we've been looking at, Q would equal the same deal there, C to the C, D to the D, A to the A, and B to the B. The deal with Q is for equilibrium, we use it when we're not sure if we're at equilibrium. So that's a lot of times one of the main reasons why we would calculate Q is to answer that question, are you at equilibrium? Remember that you can compare the Q value to the K value. And if you have a Q value that is larger than the K value, then you are not at equilibrium. And in order to reach equilibrium, which is the second thing that Q will allow you to figure out, you actually need to go to the left there and make some reactants. So those are 2 common sort of Q questions that you typically ask or one answer, which is, are you at equilibrium? And if you're not at equilibrium, which way do you need to go to reach equilibrium? Obviously, if Q is equal to K, then you are at equilibrium. And if Q is less than K, you are not at equilibrium. And in order to reach equilibrium, you need to go away from sort of this sign here, and you need to make more products in this case, right? The other place where we will sometimes calculate Q is we will sometimes calculate Q in an equilibrium problem to determine probably not the is it at equilibrium, because it probably wouldn't be at equilibrium if you're trying to determine equilibrium concentrations. But what will help you figure out again is which way the reaction needs to go to reach equilibrium. Question on Q. Also, obviously, as we talked about, you can only calculate Q if you're given all the concentrations, right? So if you're not given all the concentrations, you can't calculate Q. If you are given all the concentrations of like the reactants and the products, you could calculate Q, and that's a good indication that you should calculate Q. That brought us to equilibrium calculations. And obviously here, that is going to be, our ice table, right? So this is pretty much the calculation of the season, and the semester is ice table calculations, which obviously stands for initial change in equilibrium. And when you have initial concentrations and you're looking for equilibrium concentrations, also, if you're looking for equilibrium pressures, you could do the same calculation. You would set up an ice table like I had 2 molar of this guy, 2 molar of this guy, and nothing of this guy. If you're not given anything in terms of the products, obviously you could assume 0. You could also assume that this reaction is going to head towards the product side, which means that the change, which is ultimately the important part of this calculation, and that is usually represented with an X, we will be decreasing reactants, so those will be represented as minuses. We'll be increasing products, which those would be represented as pluses. So this would be minus x, and plus 2x. Remember that we also need to take into account, when we do an ice table, the coefficients, because that takes care of the mole-to-mole relationship, the stoichiometry to do it correctly. This is then going to just be carried down. That's going to give me a 2 minus x, 2 minus x, and a 2x. Let's just say, for example, the K value here is 50. We could do K is equal to C squared divided by A divided by B. This could go into 50. We take our equilibrium line, which would give us 2x squared divided by 2 minus x. 2 minus x equals 50. Again, you can see, hopefully it is a perfect square, and you could square root both sides and get something like this, which I won't continue out and solve, but you could solve for x in this case. When you do solve for x, that is obviously all the x's we see in this table, and that would allow you to go back obviously here and solve for the equilibrium concentrations of everybody. Again, if you're not doing concentration but pressures here, this is definitely where you need to make sure that your pressures are in atmospheres. Even if they give it to you like in torr and they want the answer in torr, it does need to be in atmospheres when you go into the ice table to do that calculation. Obviously, you'd be using a KP in this case. That is one nice way that we like to solve these problems. Maybe the not so nice way is our quadratic, right? Our ax squared plus bx plus c is equal to 0, where x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. So in certain cases, you do need to use the quadratic formula, where you cannot solve it, obviously, by doing like a perfect square. This, as we've done a number of times up to this point, will give you two x values, and one of those x values will not make sense. And the reason it will not make sense is typically when you go and put that x value in, it'll get you a negative number, and that is the one that does not make sense and you would not want to use. Then obviously you would use the one that did not give you a negative number. Remember as well that when you do this, you could get two positive numbers, two negative numbers, a positive and a negative number. So you can get any variety of types of numbers. The other way that we can solve these problems is based on our K value. So if I had a K value of 0.05, that is less than 1. And that's considered a small value of K. And when you do have a small value of K, that is the situation, and really the only situation that we can do an assumption. And we could assume in this case that X is equal to 0. That's because we have a small value of K, which means when we reach equilibrium, we should mainly have reactants. So the change part is not going to be that much, and it will be negligible. So if we go back to sort of before I took the square root of both sides and we had this situation again here, what we would do is it would be this x and this x that we assume is equal to 0. It is only the x's that you're going to subtract from somebody or add to somebody that you equal 0. Remember as well that if you make that assumption after you solve for x, after your assumption, you assume that x is equal to 0. You do need to check it, and we are rolling with the 5% rule here in this class. And to check your assumption, you take the x value you solve for, you divide it by really the kind of initial concentration, or what you're going to subtract it from or add it to, times it by 100%, needs to be 5% or less. So if you make the assumption and you do this guy after you solve for it and it's 5% or less, you're good to go. You could use that x value in your table. Remember that if it is over 5%, you do need to go back, and most likely you're going to quadratic that sort of calculation and solve it that way in that particular case. Any questions on that there? Remember as well, it is also mass. So once you get all the equilibrium concentrations, you could put it back into the K expression, and it should pretty much match the K value that was given to you. So it's a good way to check yourself at the end by doing that. Now we finish up this chapter here talking about our friend Le Chatelier's principle. And Le Chatelier's principle is the idea where you have basically a system at equilibrium, and then basically you do something to it to screw it up, basically. So you add a stress. And remember that when we add a stress, that can be concentration, that could be volume or pressure, that could be doing something with the temperature, that could be adding a catalyst. So what happens, right, in these reversible equilibrium type reactions is you do something to it to screw up the equilibrium, but it's a smart reaction in the sense that it will find a way to get back to equilibrium. And it can get back to equilibrium by shifting to the right, which means you're going to make more products. Maybe more products. There you go. You could shift to the left, which means you're going to make more reactants. Or remember that there are certain situations that even though you kind of did something to it, you can get a no change. So let's talk a little bit about what happens with each of these. Again, just a reminder with concentration, if we add, it will shift away from the side you added it to. So if you add reactants, it will shift to the products. If you add products, it will shift to the reactants. The reason for that is when you add more reactants, for example, you now have more reactants than products, which means they're going to be able to find each other and the forward reaction will occur, and that's why it will shift to the products. If you add more products, what that means is you have more products than reactants, so the products can find each other a lot easier, and that will cause the reverse reaction basically to occur. If you remove, it will shift towards the side you removed it from. So if you want to think about it like we talked about, you can make a hole on that side and you need to fill that hole. So it'll go towards the hole to fill it. What's really happening is really the same situation. If you remove reactants, you now have more products. So the reverse reaction is going to occur and go towards the reactant side. If you remove products, you now have more reactants than products. It will go to the product side and make more products. Remember that two common ways you could remove something is you make a solid or a precipitate. So you add something to the equilibrium that makes a precipitate. Or if you have hydroxide or H+, you could add either a acid or base to that, and you will make our friend water. And that's another way that you can remove hydroxide or H+ from the equilibrium by adding an acid or base to it. That is because if you remember, when we talk about the equilibrium expression, the only things that go into the equilibrium expression are things that are aqueous and gas, solids and liquids, not included in the equilibrium expression. So these guys are the only things that are included in the equilibrium expression. And again, that's why if you do either of those things, it will not make a big difference. When we talk about pressure and volume, they are sort of tied together. So if you increase the pressure, you're going to lower the volume. So the result of that is pressure goes up. You kind of want to bring it back down. So you have a much smaller volume, which means you need less gas molecules. So it will shift to whichever side has the least number of gas molecules. If you decrease the pressure, the volume goes up. So now you have a bigger volume. So to fix the pressure from going down, you need more gas molecules in that area. And that is the side it would shift to. Obviously, that is dependent on the reaction that you're talking about as to which side has more or less gas molecules in that particular case. You can also deal with temperature. And when we deal with temperature, it works the same as concentration, which means if we add, it will shift away. And if we remove, it will shift towards it. This is all dependent on what type of reaction you're dealing with, which is either an exothermic reaction, which means that energy is released, also means that your delta H should be negative. And when we think about an exothermic reaction, we think of energy and heat as being a product. That means if you increase the temperature on an exothermic reaction, it will shift to the left away from the products. And if you decrease the temperature, throw everybody on ice in an exothermic reaction, it will come towards the product side. And if you have an endothermic reaction, that is when energy is absorbed. That is a delta H of a positive number. And that is when we consider heat and energy as a reactant in this case. And in an endothermic reaction, if you increase the temperature, it will shift to the right. In an endothermic reaction, if you decrease the temperature, it will shift to the left. Remember, temperature is also really important for the value of K. It is the only thing that affects the actual value of K. So if you took K at 25 degrees and compared it to the K at 40 degrees, they would be different values. Now, if you looked at the value of K at 25 degrees for different experiments, like experiment 1, experiment 2, experiment 3, and let's just say in experiment 1, you did all reactants you started with. In experiment 2, you did all products. And in experiment 3, you did a little of everybody, little reactants and products. Remember that it doesn't really matter what you start with, as long as the temperature, say 25 degrees, for example, for all three experiments, all three K values should be the same. And remember that the ratio of products to reactants, as long as the temperature stays the same, no matter what you start with, will always equal the same ratio. We did that with that simple explanation of I wanted a K value of 2. I could do that by taking 4 divided by 2 is 2. I could get that by 8 divided by 4 is 2. I could get that by 2 divided by 1 is 2. They all equal 2. They all have different sort of numbers we started with. And that's the same idea in equilibrium. It doesn't matter what you start with in terms of how much products or reactants. You could do that reaction multiple times. As long as the temperature doesn't change, the ratio of products to reactants should always equal the same, and you'll get the same value. It will only change when you're comparing K values for different temperatures. But again, if I did 3 reactions at 40 degrees and kept it at 40 degrees, all 3 of those reactions should have basically the same K value because I did not change the temperature. Any questions on that there? The last thing we talked about in terms of Le Chatelier's principle was adding a catalyst. And remember, again, a catalyst will basically speed up that reaction, but it will cause a no change. Other ways you could get kind of a no change in Le Chatelier's principle is if you're doing something with gases and you got the same gas molecules. Number of gas molecules on both sides, that's going to be a push, and that will be a no change as well. Also, if you add something like a noble gas, which is chemically inert, it won't react too much with it, and that's another way that you could get a no change. Question on Le Chatelier's principle, equilibrium. That is the equilibrium chapter, yes. All right, so why don't we take a little break and we're going to continue on. So again, hopefully this is helpful for you. We're going to then move on to the never-ending chapter of 14, which felt like we never were going to get done with that one. So 14, if you remember, is pretty much kind of like 2 chapters in one. We kind of broke it up a little bit into kind of 2 parts. The first part was sort of basic acid-base sort of information. So we talked about acids and bases in this chapter. And remember that your basic definition of an acid is something that has the ability to produce H plus ions in solution. And what we're talking about, obviously, is the ability to produce free floating H plus ions in that solution. And that's what makes something basically an acid. Also, remember in acid-base chemistry, H plus and H3O plus, which is the hydronium ion, are basically the same thing. And they are used, as we saw, sort of interchangeable, both in formulas and also reactions as well. A base is something that has the ability to produce hydroxide ions in solution. And again, what we're talking about here, obviously, is the ability to produce free floating hydroxide ions in that solution. That was sort of the Arrhenius definition of an acid and base, something that's able to produce H plus or H3O plus. And again, when we talk about an acid, either with the H plus or H3O plus, if we take something like hydrochloric acid, which is a strong acid, it will 100% break apart into H plus and Cl minus. We could also write the dissociation of this strong acid with water being involved in the actual equation. And when we do that, what's going to happen is we're going to get that H plus that donates over, and that's going to give us our H3O plus and Cl minus. They both basically represent the same process that's happening, which is basically hydrochloric acid dissolving or deionizing in water. In this case, one just has the water there, which is what produces our H3O plus. Really what we see in the second one is the other thing that we talked about in terms of acid-base definition, and that is our Bronsted-Lowry definition. And again, an acid is a proton donor, and a base is a proton acceptor. And that is sort of the third way that an acid is sort of represented in acid-base chemistry, is we call that H plus a proton. And that is because it has one proton, one electron, and no neutrons. So in order for it to become positively charged, it has to lose an electron. So it became positively charged. The definition here, if we use this guy as an example, our HCl is definitely our acid. Water here is actually acting as the base in this particular case. And remember, sort of the consequence of the Bronsted-Lowry definition of acid and bases is we will actually create some pairs on the other side. And here, this is known as the conjugate base. And our base on one side will have the conjugate acid as its partner on the other side. Remember, in order for something to be a acid conjugate base pair, that is the only difference that you should have, which is the 1H plus difference is absolutely the only thing there. As we go again from our acid to our conjugate base, we have one less H plus because it basically gave it away. As we go from our base to our conjugate acid, it has one more H plus as it accepts the actual H plus. If it is any difference other than those two things, then they are not related to each other. They're not considered pairs. It has to be really only that difference between those two things. Remember that when we're doing this, if you had something again like maybe this and this, these guys are pairs. As the difference is only one H plus. But if you had something like this and say something like this, these guys are not pairs as it's more than one H plus. So it does has to only be that one H plus. By the way, if you're not sure when you look at the relationship between these two things, knowing which one maybe your acid or base, since the acid is sort of the thing that needs to donate it, this guy most likely would be the acid in this situation. This guy would be the base, as it does not have sort of a H plus to give. We saw and talked about the relationship between these things, and when we have an acid and its conjugate base, the relationship is if we have a strong acid, its conjugate base will be relatively weak. And if we have a weak acid, its conjugate base will be relatively strong. So as we talked about, and as we'll talk about in just a second as well, when we're talking about it being relatively strong, it doesn't mean it's like a strong base or anything like that. It means that it can continue to react, as we talked about with hydrolysis type reactions, and react with water and affect the pH. Now, when we talk about bases, it works the same way, and it's conjugate acids. If we have a strong base, we will have a relatively weak conjugate acid, and if we have a weak base, we'll have a relatively strong conjugate acid in this case. And so let's see there. I think that's good for now. I think that's what I was going to talk about. Strong acids. A reminder that when we talk about strong acids, that's your hydrochloric acid, right? Your nitric acid, your perchloric acid, your sulfuric acid, your hydrobromic acid, and hydriodic acid. So these 6 acids are considered strong acids. And again, the benefit of knowing those 6 is if it's an acid and it's not one of those 6, then it's probably a pretty safe bet that's going to be a weak acid. So, and as we know, obviously there's different calculations that she has to do if it's a weak acid, say, versus a strong acid. In terms of bases, our strong bases, as we also talked about, pretty much your group 1 and 2 on the periodic table that has hydroxide. So if you kind of go lithium down to potassium, hang it right to calcium and come down. Any of those guys in group 1 or 2 that is with hydroxide, like sodium hydroxide, potassium hydroxide, and so forth, these are typically where your strong bases come from. A reminder that the word alkaline means basic. And obviously group 1 is the alkali earth metals, and group 2, group 1 is the alkali metals, and group 2 is the alkaline earth metals. And that's, again, basically where a lot of our strong bases come from. Also a reminder that our strong bases do not have to have hydroxide in them. So the probably most popular, if you will, weak base is something like ammonia is a weak base. And when it reacts with something like water, it will actually accept the H plus there. And it will make NH4 plus and OH minus. Again, it has the ability there to produce hydroxide. And although it's not carrying hydroxide on it, it's able to do a little reaction and actually produce hydroxide, which is why it's considered a base. It's also why it's considered a pretty weak base, because if you take something like your strong base, which is sodium hydroxide, for example, it is going to be a strong electrolyte, which will 100% break apart into ions. And pretty much all sodium hydroxide has to do is go for a swim, and it will produce a lot of hydroxide really quickly. And that's going to make it pretty basic, that solution. And that's why it's a strong base. Ammonia here has got to go find some water, do a little reaction to produce some hydroxide. So it's not going to produce as much free hydroxide. So it's not going to be as strong as the base. Remember that acids and bases are also electrolytes. So strong acids, strong bases are strong electrolytes. They 100% dissociate or break apart in solution, while weak acids and weak bases are weak electrolytes, which means they mainly stay together. So again, if you have something like hydrofluoric acid, which is a weak acid, by the way, I know that by process of elimination, it's not one of those, which is a strong acid, it's going to break apart into H plus and F minus. In solution, you're going to mainly have this guy together, but you will produce a little of those guys. So you'll mainly have the HFs together, but it will produce a little H plus and F minus. So since it's able to still produce a little bit of that H plus, it's still considered an acid, but definitely a weak acid compared to HCl, which will just completely fall apart and produce a lot of H plus really, really quickly in that solution. Any questions on that there? That brought us into how to determine, again, if a solution is acidic, basic, or neutral. And remember that there are amphoteric substances, which can act as an acid or a base. And one of those is actually water. Water can act as an acid or a base and will break apart into, I don't want to bracket it here. Get rid of that. We'll break apart into H plus and OH minus, or H3O plus and OH minus if you like. And this is an equilibrium, which of course, obviously we could set up an equilibrium constant for it, and that is our friend Kw, right? And that is the ionization product there of water. That is the concentration of H plus times the concentration of OH minus. And that does equal 1 times 10 to the minus 14. Remember, it is an equilibrium constant, which means it is affected by temperature. So if you happen not to be at 25 degrees Celsius, the Kw would probably be a different number. But I would say probably 99 times out of 100, it's going to be that number, unless they specifically kind of tell you that, and they'll give you a different value to use. We could use this basically, it's the same calculation regardless of which one's given to you. You take the H plus concentration you're looking for, take 1 times 10 to the minus 14 divided by the OH minus concentration. And you could also calculate the hydroxide concentration by doing the exact same calculation, 1 times 10 to the minus 14 divided by the H plus concentration. We could use these concentrations to compare and see if it's acidic, basic, or neutral. If our H plus concentration, which means our acid part, is greater than our OH minus concentration, or base part of the solution, it is going to be acidic in this case. If our H plus concentration is equal to our OH minus concentration, then it is going to be neutral in this case. And lastly here, if our H plus concentration, which means our acid part, is not as big as our hydroxide or base part, it will be basic. Remember that these guys are tied to each other, which means as the concentration of H plus goes up, concentration of OH minus goes down. And as concentration of OH minus goes up, the concentration of H plus goes down. So again, they're sort of opposites of each other. The more you have of one in the solution, the less you have of the other, which is why it's going to be either acidic, basic, or neutral based on that there. Now, this is one way we can determine if the solution is acidic, basic, or neutral. Definitely, as we've talked about many times, you want to definitely make sure exponent button being used when you type these things in, right? So make sure you're definitely using your exponent button on your calculator so that you do get the right answer. Also, the other thing to remember as well, which is a common mistake that people make when they go to compare these two things, the exponents. So if you have 10 to the minus 6 versus times 10 to the minus 12, the larger one is the smaller negative exponent, right? So that is your larger guy. The negative is important there because you're going to go to the left and add a bunch of zeros, right? So the guy in the bottom there, you're going to add like 11 zeros, and the other guy, you're only adding about 5 zeros. So the smaller the negative exponent, the larger the number actually is. So again, that's an important sort of error that sometimes people make. We then talked about really the most common way that we kind of deal with is it acidic, basic, or neutral is our pH scale. And we use our pH scale. And again, it runs from 0 to 7 to 14. And below 7 is acidic, above 7 is basic, and dead on 7 is neutral. And dead on 7 is neutral technically because that is really the point where the H plus concentration and the OH minus concentrations equals each other, and they both would have a concentration of 1 times 10 to the minus 7, which means that would give you a pH of 7, basically. So that is technically what it is. As you go from 7 towards 0, it is more acidic. Go 7 to 14, it gets more basic. We could calculate the pH by taking the pH is equal to negative of the log of the H plus concentration. Again, a reminder, much like the KW as well, you can write it H3O plus if you like. And you could also, again, use that H3O plus in the KW. We talked about the importance of knowing how to punch this into your calculator correctly. So one more final reminder, if you have a display calculator, you are going to hit the negative button, the log button, and your number. If you have a non-display calculator, this one, and again, all the rest of them, you're going to work backwards. So you would start with the number, you would hit log, and then you would hit your negative button. Again, if you're not sure what type of calculator you have, hit the log button. And if it says log on your screen, you have a display calculator. If it says error on your screen, you have a non-display calculator. So that is the way you can do that. Now, the pH tells you, what you need to calculate it. H means you need the H plus concentration. The pH goes down as the concentration of H plus goes up and the concentration of OH minus goes down. The pH will go up as concentration of H plus goes down and the concentration of OH minus goes up. So that is the relationship that you got going on in that situation. Now, the pH scale and the pH should not be confused with the other sort of calculation we talked about, which is the pOH. Much like the pH, it tells you what you need. OH means you need the hydroxide concentration minus the log of the OH minus concentration. You would type it in your calculator the exact same way as you would do pH. Remember that if you're thinking about the pOH scale, which most people never think about the pOH scale, it goes from 0 to 7 to 14 as well. But below 7 is actually basic. Above 7 is acidic, and 7 is still neutral. It is opposite of the pH scale. So again, as I mentioned many times, there is only one right answer for that question of, is it acidic, basic, or neutral? Cannot be all three or two of the three. Should only be one of the three. So I would always recommend looking at the pH scale because that, again, is the one that most people have in their head. Again, don't be the person on the final that goes, this solution is acidic and basic at the same time because you calculated the pH above 7 is basic, and then you did the pOH is less than 7 and you said it's acidic. So again, only one answer. I would probably recommend not looking at that scale so you don't screw it up. Why would we want the pOH other than calculating the pOH? There is a nice relationship, right? You could take the pH plus the pOH, and that does equal 14. So that does give you some options in terms of how you might want to calculate something. If you have, for example, the hydroxide concentration and you want the pH, you can get the pOH and then take 14 minus it to get to the pH. If you want to, you could still take the hydroxide concentration and use Kw and get the H plus concentration, and then use the H plus concentration to go into the pH and get the pH that way. So it does give you a variety of sort of options as to how you can sort of calculate this stuff. Added to that is a couple more sort of formulas that we talked about and ways that you could calculate some of these things. If you have the pH given to you, you could directly get from that your H plus concentration. So directly from that, you could take the inverse log of the minus pH. Again, on most people's calculators, when they punch that in, that's a 10 and a caret in a negative pH. You could also, if you have the pOH given to you, you could get directly from that the OH minus concentration. It is the same calculation, the inverse log of the negative pOH. Again, a 10 and a caret negative pOH. And a reminder, calculator-wise for this, most people, that's going to be a second button, upper left corner of your calculator, or shift, then a log button, and then a negative button, and then put your pH or pOH in there if you have a display calculator. If you have a non-display calculator, you again got to start with the pH or pOH number. You then actually need to make it negative. Then you need to hit the second or shift button and then the log button. Yeah, and then that will get it for you there. So whichever way you go, you can calculate that. So it does give you a variety of options depending on what information you're looking for and what you have. You could use everything from Kw to the pH to the pOH to the pH plus the pOH equals 14 to the sort of inverse log calculation to solve for whatever you may be sort of looking for. Any questions on that there? Now, continuing on here in this chapter, we talked about a couple of things. Let's see, what did we talk about? We talked about the pH of strong acids and bases, strong bases. So because they're strong acids are strong bases, the acids are pretty straightforward. Remember, if you had something like HCl and it breaks apart into H plus and Cl minus, it is basically, if this was 0.025 molar, it is a 1-to-1 relationship between those two, which means the concentration of our H plus, which is really what we need for our pH equation, would also be 0.025 molar. So that would allow you to go directly into your pH equation minus the log 0.025. And we'll do a little minus log here, 0.025. It's going to give us a 1.602 in this case, which is acidic. Why did I go so far in terms of my decimals? It is the rule that we talked about. The concentration here has 3 significant figures. That translates to 3 decimal places, right? So remember that when you calculate the pH or pOH, however many significant figures the concentration has is how many decimal places your pH or pOH value should have. So in this particular example there, I have 3, and I would need 3 decimal places, not significant figures. Now, I would say for your strong acids, you're probably going to be in pretty good shape, because if you look at that list of 6 strong acids, pretty much most of them are monoprotic, which means they can only donate 1 H plus. So whatever the concentration of the acid is the concentration of the H plus. Now, bases works the same way. If you had KOH, it would break apart into K plus and OH minus. And let's just say we have the same concentration here. It would be a 1-to-1 relationship between those two in terms of the hydroxide, which would give us 0.025 molar here. Remember that this is hydroxide and not H plus, which means really you could calculate the pOH in this case, minus the log of 0.025. And again, that's going to give us our same value that we got over there, which was 1.602. But if I want the pH in this case, we're going to do a little 14 minus our 1.602. And we would take, we'll call it 12.4 in this case. That is definitely basic, which is what we would expect with something like potassium hydroxide in this particular case. So remember that if you're doing this for a strong base, you're going to get, again, the hydroxide concentration, which means you do need to go pOH first and then into the pH in that particular case. Remember, you might have to adjust it. I think maybe we did calcium hydroxide in one of our examples in our notes. And when this breaks apart, you do get a calcium ion and a couple of hydroxides. So whatever this guy's concentration would be, I'll just add an extra 0, I guess. We would actually need to multiply that by 2 in this case to get the proper concentration. That's what you would go into the pOH equation with. Any questions on strong acid or strong bases pHs? That led us into our discussion of weak acids and really weak bases, because gosh forbid we missed equilibrium at that point. So we can have a weak acid, and a weak acid will break apart like hydrofluoric acid, for example, but it will mainly stay together and will create this equilibrium reaction. A reversible reaction is going to happen. And that means because it ultimately is an equilibrium, we could write, of course, our equilibrium expression for it, which is known as a Ka, and that would be our H plus and our F minus divided by our HF in this case. Now, if we wanted to figure out the pH of this, we would have to do a little bit different, obviously, than a strong acid or a strong base. But when we talk about a Ka value and we compare a Ka value, the larger the Ka value, the strength of the weak acid increases. And that is because if I have a large K value, that means, as we normally know, that we should have mainly products at equilibrium, right? So I should mainly have products at equilibrium. And in this case, my products is H plus is one of them. And that means that I would have a larger amount of H plus at equilibrium than if I had a smaller K value or Ka value in this particular case. Now, we solve these type of problems just like we solve any regular equilibrium problem. So you do need to do an ice table if you want to figure out the pH, for example, of our HF. And again, you would run through your ice table. You would probably have an initial molarity here. You would zero these guys out. This is going to be a minus X plus X situation. We'll take our initial molarity minus X, X, and X. Clearly, this would go into our Ka expression. Obviously, we'd put all these guys in. And here we would solve for X. Now we would solve for X in one of the three ways that we normally solve for X in an equilibrium situation. Maybe you get lucky and it's a perfect square. You might need to do the quadratic to solve for X. Or in this case, you could try the assumption and maybe it would work as well. But once you do solve for X in this case, it varies from a normal sort of equilibrium calculation because usually we're interested in the pH. And usually X will equal the H plus concentration, which means you could then go directly into your pH and actually calculate the pH in this particular case. Any questions on that there? Remember that when we're doing these type of problems, we also talked about percent ionization. And if you did make that assumption, again, you would need to check it. And a reminder that really the percent ionization of an acid or a base is really, again, the check that we do to make sure it's okay. It is the concentration of H plus divided by the initial concentration of your acid times 100%. And that is the way that we check our assumption. And it's also really the percent ionization as well. Now, when we have something that's a strong acid or strong base, it is 100% ionized, which means it completely breaks apart into ions. You have no whole units together. So if you're 100% ionized, and it's like hydrochloric acid, this is all you got floating around are ions. You have no HCl units still together. Now, the percent of ionization is dependent on the concentration of your acid. And that's why in some cases the assumption works, and that's why in other cases the assumption does not work. And a reminder that if you have a large initial concentration, you might remember my pizza example. That's a wonderfully drawn non-topping pizza right there. So here, if we take out just one slice, we still have a pretty good amount of stuff left. It's not that big amount of my pizza. But at the end of the day, when clearly there is only 2 slices of pizza left on the tray, you sneak that one piece out of the way when nobody's looking to see that you did that, and you leave just one piece of pizza left. You're going to have now taken a greater percentage of what you started with, right? So you took 50% of what was there rather than maybe like 1/8 of what was there, depending on how many pieces you have. So the larger the initial concentration of your acid, the little bit that comes off is not going to be a big deal. And that's why your assumption is 5% or less. If it's less than 5% of that, then it's all good. You could do it. If it is a smaller concentration, then when you do that sort of assumption, it will be a bigger percentage and it will not be negligible. That's why if you go back in your notes, I think we did one that was like 0.5 molar HF actually. And then we went and did like the assumption there of 0.0510 fold less. Assumption no good here, but was okay here. And again, that's because of the difference in the concentration. The little bit that comes off is going to be pretty big. By the way, that is also why when we do the assumption, and what this is really based off, and we take the number minus, X, that is the one we get rid of because we already have something. So what comes off is not going to be that much. That's also why we don't zero out when we start with 0 and we just end up with like 2X at the bottom. Whatever we get when we started with 0 is significant because you started with nothing. So whatever you make is going to be significant. So that's why we don't zero out those guys. You could just straight up calculate the percent ionization by plugging and chugging into that equation. We could also use it like we did in one of the examples we did in class, which was if you know the percent ionization, you could back calculate something like the equilibrium constant from knowing that information, because that will allow you to figure out the H plus concentration and ultimately allow you to figure out really what X is. After that, we talked about similar weak bases. And again, weak bases work the same way. Again, if we look at something like ammonia, which is a weak base with our water, accepting. And if you want to, you could write ammonium hydroxide together or keep it separate. We would have a K expression here, which is known as a KB expression, B for base. Still the same thing here, our products over our reactants. Here we're not going to include water because it's a paired liquid in this case. And again, in this case, it works the same idea as the Kb value increases. The strength of that weak base will also increase as well. Again, it's nowhere near as strong as a strong base, but in terms of comparing a weak base to a weak base, it would be higher. The reason for that is the same reasoning. If you have a large Kb value, you mainly have products. You mainly have products, you have a lot of free OH minus, and that is basically your definition of a base in this particular case. We're going to ice table this guy up as well if we need to do some type of equilibrium calculations. A reminder that the difference here is when you do solve for X, however you're going to solve for X, that is going to be the hydroxide concentration and not the H plus concentration. So that means in this case, you typically need to go POH root first, and then you could subtract 14 there and get yourself to the pH. So remember that just because you solve for X in these situations, it may not be the H plus concentration. You want to make sure if you're going to calculate pH that you do have the proper H plus concentration. How do I know if I should use a Ka or a Kb value? We talked about a number of ways, but again, a reminder that, if you look at the product side of your equation, which is why, as we talked about, it's important to know how to write these equations, and you see either H plus or H3O plus by itself, that means you should probably be using a Ka in that calculation. If you look at your equation, you write it correctly, and you got hydroxide happening there on the product side, that means that is probably a Kb calculation that you definitely should be using. What happens if you need a Ka or a Kb and you don't have them, but you do have one of them, either a Ka or a Kb? Remember that you can take our Kw will equal the Ka plus the Kb value in this particular case. That is because if you have a weak acid, which would be something like this, Ha goes to H plus and A minus, as that's just a generic acid, that would be a Ka value. Take a base plus a little bit of water here. Going to give us here Ha and hydroxide, in this case, Kb. That is adding two equilibrium reactions together. Going to cancel out things on opposite sides here. That's going to leave me my water. And as we talked about, to calculate Kw, or to calculate an equilibrium constant, if you add up two of these together, you multiply those values together. So that's why we multiply our Ka times Kb in this case. And again, you can see clearly here, H plus should be Ka, OH minus should be Kb. So that is the way that we can basically go from one to the other if we need to. A Ka will equal basically Kw divided by Kb. And again, the Kw is that 1 times 10 to the minus 14 number that we used previously. The Kb would be our Kw divided by our Ka value in this particular case. That led us into talking about a situation where this is very common that you need to use that equation, and that is in hydrolysis problems. And when we react an acid and base together, we produce two things. We produce typically water and a salt, right? So if we produce or react hydrochloric acid with some sodium hydroxide, which is an acid-base reaction, it is a double displacement reaction where these guys are going to switch partners. That will produce water, the H from the acid, the OH from the base, and a little sodium chloride. So that is my salt. That is my water. A salt's just a fancy word for an ionic compound. This salt here basically came from, if we had this salt, it came from a strong acid and a strong base. And basically what that means is this is considered a neutral salt, where the pH should be 7 if you have that in solution. And that is that relationship that we talked about earlier, that if you have a strong acid, its conjugate partner will be weak. And if you have a weak acid, its conjugate partner will be strong. And if you have a strong base, its conjugate partner will be weak. So typically speaking, anybody from group 1 or 2 on the periodic table is a neutral salt. And that is because, as I mentioned earlier, that is pretty much where a lot of your strong bases come from. So anybody from group 1 or group 2. Any negative guy that comes from a strong acid will also be neutral, and the pH should be 7. You don't have to really do any calculation in that case because it should be basically a neutral salt. But if we have a salt that comes from, say, a weak acid, like if we have acetic acid and sodium hydroxide, again, going to do a double displacement reaction here. And that's going to get us water and sodium acetate in this case. Again, that's going to be our water, and that's going to be our salt in this case. That salt, which is really the sodium acetate, will break apart in solution and break apart into a sodium ion and an acetate ion. And remember that when you're looking at a salt to try to determine whether or not it will basically go through hydrolysis, what you want to know is where it comes from. So that's why knowing kind of where they come from is really good. Also remember that you're typically given a lot of times in these problems a Ka or Kb value, which is technically where these guys come from when you look at. Sodium we're not going to worry about because it is group 2 or 1 on the periodic table, but really 1. The acetate we do have to worry about because it does come from this acid, which is a weak acid. And because that's a weak acid, that means that this guy would technically be its conjugate base. And that means it will go through the hydrolysis reaction. It will react with the water that's sitting there, basically. And you will get a reaction of your salt plus your water. And if you're not sure what's going to happen, use the idea that that should be a base. And the definition of a base is it's going to accept the H plus. So it will actually accept the H plus in this case. And it will always form where it came from. So it will form acetic acid, which is basically where that salt came from. And you will form hydroxide in this case. That formation of hydroxide is really important because that's going to tell you this guy is going to be a base. Also should tell you that if you do the ice table calculation, if you want to know what the pH would be, that should also be a Kb that you need in this particular case. So these are, again, typically the problems that you are given the wrong K value to use. They give you the Kb when you should have the Ka, and vice versa in this particular case. So this would be a situation where you would get the the Kb, by taking the Kw divided by Ka. In this problem, they probably gave you the Ka value of acetic acid. In this case, you would solve for X, and once you do that with the Kb value, that is going to equal the hydroxide concentration, which will allow you to calculate the pOH and then calculate the pH. So again here, this is why it's going to be basic. You're producing hydroxide, and you can actually calculate how much hydroxide you're going to produce. Any questions on that there? Now, we also have salts that are acidic. So salts that are acidic basically come from a strong acid and a weak base. So for example, if you took something like NH3, which is again our weak base, and hydrochloric acid, which is a strong acid, again, we will make here NH4 plus and Cl minus. You can put it together if you'd like and make ammonium chloride, but I'll keep it separated here. This once again will give us basically, we have a weak base and a strong acid. That's going to give us this guy, which really is ammonium chloride if you just slap it together there. And again, that's a strong electrolyte, which is going to break apart into these two things. Here, we're not going to worry about the chloride because it comes from the strong acid, which means it's going to be relatively weak. But our NH4 plus comes from this weak base, which means it is going to be relatively strong and it's going to be an acid in this case. So if you're not sure, that is how you know that when you take your NH4 plus and you react it with your water, it is going to act as the definition of an acid and it's going to donate the H plus over, and you will get your NH3, which is where it came from. And here we will produce H3O plus. And once again, it is that production here of H3O plus that before you even do a calculation, you should know that it's going to be acidic in this particular case. And with that being said, you're probably going to be given the Kb value here. You'll need to use Kw to get it into a Ka value that you need. And again, you would do an ice table here. You would solve for X. In this case, though, X is going to equal the H plus concentration or H3O plus concentration. And that means you could actually go right into the pH on this particular one and get it. So that is an acidic salt that comes from basically a weak base and a strong acid sort of reaction. Any questions on that there? The second way that we saw, and we had some in that experiment that we did, that you could generate sort of an acidic salt is with metals. So if you have relatively small metals, transition metals that maybe are surrounded by water, that's another very common way that you can produce an acidic salt. I think we looked at aluminum, which is not necessarily a transition metal, but transition metals will work the same way. So if you got some waters attached to it because it's hydrated, I'll just draw one of the waters out. And you got really this complex ion, which nowadays you know how to name properly, I suppose. 3, 4, 5, 6. So what happens in this situation is you have just a regular old water coming on by, and it's going to pluck off basically one of those hydrogens on the water that's attached to the metal in that complex ion. The result of that is that's what's going to give you on the other side of the arrow some H3O plus. And because it's going to generate some H3O plus, that's going to get you basically an acidic salt. Any questions on that? Speaking of acids, we also talked a little bit about acid strength, right? And a couple of ways you could kind of compare acid strength. If you're dealing with acids that do not have oxygen, like HF, HCl, HBr, and so forth, it is actually bond enthalpy, our energy. That is the most important thing to look at. And when you go up group 7, which is pretty much what you're looking at there, as you go up group 7, the bond energy increases. So the bond energy increases. And that's really important because if you just take HF, for example, in order for this guy to fulfill its duties as an acid, it's got to break that bond and release that H plus into the solution, basically, right? So it could go for a little swim. And the only way to do that is to break that bond. And if the bond energy is really strong or really high, it's going to take a lot more energy to break that bond, which means not a lot of that H is going to come off. The bond energy down here between, say, H and I is much less. And because that bond energy is much less, this H is more apt to come off. And it makes them for a much stronger acid in that case. So when comparing acids that do not contain oxygen, you want to look at bond energy. Stronger the bond energy, weaker the acid, kind of the weaker the bond energy or enthalpy, the stronger the acid. When you're dealing with acids that have oxygen, you look at one of two things. Either you look at the oxidation number or state of the central atom, or you look at electronegativity. So, for example, I think, I don't remember, HBrO3 maybe, and we had HClO3, two of these acids. And when we look at these guys, in terms of their oxidation number, that's going to be -2, which is -6. That's a +1. That's a +5. Here, that's a -2 is -6. That's a +1. That's a +5. So they both share basically the central atom in these acids. They both share the same oxidation number. So you can't use that to decide. So what you would then use is electronegativity in this case. And the higher the electronegativity, the stronger the acid. And the reason for that is kind of the same idea. Oops. Oh, and no, I won't fully draw it out, but you basically have this bond here in an oxyacid, and the stronger the electronegativity, this polar bond is already going in this direction in terms of this electron, and if the more electronegative here is in the middle, it's going to bring the electrons in even further. That's going to continue to weaken and weaken this bond a lot more. You can make it a lot easier for this guy to pop off, basically. And the greater electronegativity, the stronger the acid. The lower the electronegativity, the weaker the acid. Now, when you do have two acids that have oxygen and you want to compare which one is stronger, in this case, you would actually look at the oxidation number. Since they're both the same element in the middle, we have -2, which gives us -4, +1, that's a +3. Here, again, we had our -6, our +1, that's a +5. So it's the same idea here. In each of these cases, we basically have at some point this bond. We have the other bonds as well, but we'll just look at this bond. With this guy at a +3 versus a +5 here, same idea. Electrons, because its polar is coming this way, with the +3, it's going to bring it in a little bit more. Electrons coming this way because it's polar bond with a much higher positive charge, going to bring the electrons in a little bit more. That's going to weaken this bond more than it's going to weaken that bond, and going to allow this guy to come off a lot easier and going to be a stronger acid. Any questions on that there? All right, then lastly here in this chapter, we talked about two other definitions, or this first half of this chapter. We talked about Lewis acids and Lewis bases. And a reminder that Lewis acids and Lewis bases deal with Lewis there and electrons is what we're talking about. And a Lewis base that we saw later on in a chapter down the road is something that will donate a pair of electrons. Those are our friends like water. Got some electrons to donate. Cl minus. Have those things to donate. A Lewis acid is something that will accept a pair of electrons. And that is usually something that is electron deficient. And that is basically what our complex ions that we talked about basically deals with, right? We have a complex, in a complex ion, we have a metal that's in the middle that's positively charged. And usually if you're positively charged, then that means that you are electron deficient. And that's going to allow you to want to accept electrons. So If you had something like boron, which is a incomplete octet, it will be more apt to basically accept those electrons from something like ammonia, which is a good Lewis base. Any questions on that there? All right, that is the first half of chapter 14. It felt just as long the second time through, I think, as well. So what we're going to do is we're going to lay it up there for now.